interrogating.
Okay, our last talk of the session is about ASIC resistance of Equihash, and the talk will be given by Jen Gao. Okay, let's welcome Jen. Claro? Okay.
So hi, I'm Jian Gao, and here we are trying to construct an adversary solver for Equihash, the proof-of-work system. This is a joint work between Xiaofei Bai, myself, Chenglong Hu, and my advisor Liang Zhang. A little bit background. We all seen proof-of-work working in cryptocurrency systems. This is not the only way to operate them, but is still one of the acceptable ways. In these systems, one of the most important considerations is fairness. Say, if you ask for 1 kilojoule worth of work, you don't want someone to get around with just 1 joule worth of work. More specifically, you don't want the adversaries to have this ability while your honest users do not. Being unfair, you're asking the adversaries to cheat in your system, and they could eat away your miner profit, they could drive your miners away, and they could possibly form monopoly and sometimes practically launch 51% attacks. So, how do adversaries actually cheat? They build specific hardware to solve these proof-of-work problems, and the latest technique they use is the ASIC solvers. It's not the ASIC solvers themselves causing problems in the systems. It's the adversaries building and using them while not letting the honest users a chance to even buy one. Say, when an adversary has such a product, he would not want to let other users have it because that would take away his efficiency advantage and take away his profitability. There are alternate methods exist one obvious approach would be to try to limit ASIC solvers by crafting the proof-of-work puzzles with special characteristics. And in fact, this approach has spawned almost every single proof-of-work schema after the SHA-256D as used in Bitcoin. And nowadays, building these solvers is actually significantly harder. There's also other methods to, say, make ASIC solvers not profitable rather than not technically impossible. Say, Monero tweaks its proof-of-work schema every 6 months, so already built ASIC solvers can't work anymore. More on this topic, if you're interested, you can refer to our paper. Following these approaches, Equihash is a proof-of-work schema published 3 years ago, right here at NDSS, using a modified version of general birthday problem in its core. Despite a few optimization techniques found in the recent years, it has generally worked very well in systems including Zcash and Bitcoin Gold. There actually are some highly efficient ASIC miners out there that can handle its smaller by memory consumption, smaller parameter sets like 200 bits over 9 rounds, but these miners cannot tackle the larger parameter sets like 144 bits over 5 rounds. In our project, we're going to tackle these larger ones and eventually building a design not sensitive to the parameter changes. This project kind of started as one of my random ideas that efficient ASIC solvers might still be possible for ASIC resistant schemas. where computational cost is dominated by some factors out of the logic core and is shared between all the different solver designs, be it ASICs, CPUs, GPUs, FPGAs. And we found that the state-of-the-art proving approach is not quite sound as it might seem. So we decided to actually craft such a adversary solver to demonstrate it. Doing so is not easy and not especially meaningful considering the larger parameters are undeployed very widely, but make sense to demonstrate how adversary actually builds these solvers to understand what is causing problems for them and how do they work around these problems, and at the end of the day, we'll probably be able to design proof-of-work systems with better fairness and possibly to offer better protection to the underlying systems. So let's look at the honest solving algorithm and see what we could do. On the top, marked in black, we need to, step one, we need to generate some pseudo-random numbers to feed to the component. And step two, the red part, we need to find all pairs that collide on given bits. This is going to be a lot of RTL programming, but we'll talk about it later. And step three, marked in blue, we need to compute exclusive OR in each found pair to be the new input for next round. This is going to possibly be easier implemented in hardware even compared to software. Tackling the red step, the step two, the drawing step, is not going to be easy because under large parameter sets like 144 bits for around five rounds, both the list itself and the recording of index are too large for on-chip storage and should go to off-chip memory where accessing them is both slow and energy expensive. Honest software solvers typically use a hashing strategy. We can do hashing with hardware as well, but that would mean we'd be basically stripping unused logic from CPUs and GPUs and won't have much advantage. So, or we can try a linear time sorting approach. So if is there a sorting method more efficient than hashing? Well, yes and no at the same time. I say yes because on ASICs, all the data can move around simultaneously running in different logic components and doing their own jobs. Taking this advantage, we can build a smart cell for sorting with 2 sets of flip-flops and 1 comparator. Every single tick, data entries move 1 step through the smart cell with the input saved internally and the previously saved entry moving to the output. If and only if the input is greater than the saved one, it takes a jump ahead and gets sent to the output instead. This one is easy, but when we chain these smart cells together, we can actually sort longer lists because the greater values will always overtake lesser ones and eventually form a full sequence. In the worst case, where the greatest value enters last, but it has to exit first, we would need to have n smart cells to practically sort an item list. And that's why I previously said to the question, I said yes and no. Because now we have a very graceful linear time sorting module that only takes a single sequential read, but it calls linear logic. And under popular parameters, the sequences to sort are typically millions to several hundred million of items long. And such a sorting module would be too large to fit on a single chip and could possibly use kilowatts of power and is not practical at all, let alone profitable. To combat this, sequences need to be much shorter, and we add a merge step afterwards. The sorted data from smart cells need to be written to memory and read back again, because the output pattern and the input pattern of these components are different. The smart cells output sequentially, whilst the merge component access data pretty much randomly. Memories have latency, and the merge modules could stall and clog up the whole solver pipeline, which is bad. We need to have, we can't really cache the input because it is random. We can, however, prefetch them, and we can add prefetch queues on each merging lane to keep the merge module fed. This will likely be implemented with SRAM or EDRAM blocks, and if that's still too slow, we can prefetch them again into flip-flop storage. Now that the list is sorted, we need to generate some colliding pairs and record their index and compute the exclusive OR values. The task itself is trivial with, say, embedded MCU, but the length of the output list will be problematic this time. The length will actually be random only with, we only can know it is mathematically expected to stay the same. It's okay if the list could shrink, we just add bubbles into the pipeline and it would just work. But if it expands, we can't sort correctly in the next round. These cases are actually the these cases with more intermediate entries are actually better ones from the adversary's point of view, as they tend to yield more solutions, but handling them is totally unrealistic, and their appearance is totally virtually impossible. It may have trillions of pairs, and there's no reason to handle them. Sooner or later, we'll have to cut the tails from the list somewhere, since most of the time the length will stay the same around this mathematical expectation. This will hurt the total yield, but it won't hurt a lot. So where are we at? By now, we have constructed all the major modules in our adversary ASIC solver with Smartcell-based sorting, with merging and prefetch, with pair generation, with MCUs and tail cutting. We need a method to evaluate our design and test out different configurations, like how do we merge, where do we cut tails, and how far should we prefetch. We can prove the algorithm is correct because it is still the honest algorithm. It's fundamentally unchanged. We can verify our implementations via simulation, which we did for all of these core components. We can calculate its memory usage to make sure it's possible. We can calculate performance in a similar way, but we cannot know its exact frequency and power usage without taping out the actual solver core. This is the same problem real adversaries are facing. Taping out chips are time-consuming and expensive. If they can't be sure they're profitable, they won't want to tape it out. But more on this topic later. As of memory, our example configuration will be using less than a gigabyte under 209 and at a speed of tens of gigabytes per second, depending on frequency. Or under 144, we'll be using a few gigabytes at a similar speed, but both are in the range of commercially available memory products. As of power, the microelectronics engineering toolchains include software to estimate power usage based on the design, the choice of clock speed, and a tech library. These estimations serve as references for IC designers, so they're good enough for us, even though they are not exactly accurate and will not reflect the eventual product. So we borrowed these tools, namely Synopsys, Design Compiler, and a 28 nanometer high K metal gate tech library and ran it for all our core components, giving us a 1.5 to 2 watts or power usage under 1 gigahertz core clock. This scales very well to with frequency, so when we set the frequency to higher or lower, we can just multiply it. Finally, we're able to calculate our overall efficiency. We take our frequency measured in cycles per second divided by the worst case pipeline behavior in cycles per round, divided again by K, which is rounds per puzzle, multiplied by the theoretical yield in solutions per puzzle, and we can consider the percentage loss from tail cutting, finally divided again by the power consumption in watts, resulting in energy efficiency measured in solutions per joule. At 500 megahertz core frequency, we can get around a little more than 10 times efficiency advantage over honest software solvers. There are some factors and overheads that could add bias to the results, and we discussed them within our paper, but in all, it is safe to predict that ASIC adversary could get 10 times efficiency advantage, that's 10 times a profitability advantage. To sum up, we have constructed a highly efficient ASIC adversary solver design for Equihash to work on all its parameter sets. We think that we actually recommend that the related systems and assets should be carefully valued again. We expose the design procedure of adversaries to demonstrate that these proof-of-work routines, be them real-life algorithms or cryptographic operations, however they are proved to be ASIC resistant, they are easily subject to tweaks and optimizations. To provide a sound proof of ASIC resistance is really hard, if not at all possible, if not impossible. I think this can conclude our findings, and thank you for your attention. I'm happy to take any questions.
Okay, I have a question. What do you think your future work would be along this line of research?
The major part will be we try to go deeper into how the adversaries face problems and utilize these problems to construct to construct proof-of-work systems with more fairness. We want to utilize them to block them further.
Thanks, speaker again, and also thank all 5 speakers of the session. Okay. Well, I think our